The universe hides monsters of pure gravity. We are about to explore 30 black hole facts that will permanently change how you see reality itself. By the end, you will not look at space, time, or even the concept of information the same way again. We will journey from cosmic giants that swallow light to puzzles that threaten the foundations of physics. From the sound of a black hole to the possibility of seeing the entire future. What do you think is the most unsettling truth about our universe? The very name is a cosmic misdirection, a trick of language that paints the wrong picture entirely. A black hole is not an empty void, not a hole in the fabric of space. It is instead the exact opposite. Imagine taking the mass of 3 or 4 of our suns and crushing it down into a sphere just 12 miles across. That is the level of density we are talking about. The result is a region of spacetime where gravity becomes so overwhelmingly powerful that the escape velocity, the speed you would need to travel to break free, exceeds the speed of light. Since nothing in our universe can go faster than light, nothing, not a single particle of matter or a single photon of light, can ever come back out. This creates what we call the event horizon. Think of it not as a hole, but as the ultimate point of no return, an invisible spherical boundary. Once anything crosses that threshold, it is gone from our observable universe forever. A helpful way to picture this is to think of spacetime as a stretched trampoline. If you place a heavy bowling ball in the center, it creates a deep, curved depression. A black hole is like taking that same bowling ball and shrinking it to the size of a marble while keeping all its weight. The depression becomes infinitely steep, a bottomless pit in the fabric of the trampoline itself. That pit is the black hole, a sphere of ultimate density, not an empty hole. This means the darkness we associate with a black hole is not the darkness of an empty cave. It is the darkness of a prison from which even light cannot send a message. That profound density manifests across a staggering range of scales. Black holes are not a one-size-fits-all phenomenon, but come in distinct cosmic classes. The most common are stellar mass black holes. These are the remnants of massive stars, at least about 20 times heavier than our Sun. When such a star exhausts its nuclear fuel, its core collapses catastrophically in a supernova explosion. If the remaining core is heavy enough, nothing can stop the collapse, and it crushes itself into a black hole. These are relatively small, with event horizons perhaps only the size of a major city, yet they contain the mass of several suns packed inside. Then we have the true titans, the supermassive black holes. These monsters, weighing millions to billions of times the mass of our Sun, reside at the very heart of nearly every large galaxy, including our own Milky Way. Their scale is almost incomprehensible. The event horizon of a typical supermassive black hole would engulf our entire solar system out past the orbit of Pluto. Imagine a gravitational sphere that large, with a density at its center that defies all logic. How such behemoths grew so big, so early in the universe, remains one of astronomy's greatest puzzles. Bridging the gap between these two extremes are the elusive intermediate mass black holes. Weighing perhaps hundreds to hundreds of thousands of solar masses, they are the missing link, suspected to lurk in dense star clusters or as the seeds from which supermassive giants grew. Finding them has been a cosmic detective story, with only tantalizing clues hinting at their existence. This hierarchy reveals a universe where gravity sculpts structures from the size of a metropolis to the heart of a galaxy. But what does one of these cosmic monsters actually look like? The iconic image released in 2019, A fiery orange ring with a dark central shadow was not a photograph in any conventional sense. It was a monumental achievement of human collaboration called the Event Horizon Telescope. This was not a single telescope, but a planet-sized virtual instrument created by linking 8 radio observatories across the globe, from Hawaii to the South Pole. For days, they all stared in unison at the same point in space, the supermassive black hole at the heart of the galaxy Messier 87. What they captured was not visible light, but radio waves emitted by the superheated gas swirling at nearly the speed of light in the black hole's accretion disk. The dark shadow at the center is the black hole's event horizon, or more precisely, the silhouette it casts against that brilliant background of doomed matter. That shadow is about 2.5 times larger than the event horizon itself, warped and magnified by the black hole's extreme gravity. This image, a painstaking reconstruction from petabytes of data, was a direct visual confirmation of Einstein's predictions. It proved these objects were not just theoretical phantoms, but real, physical structures shaping the cosmos. The true marvel was the global synchrony required, a moment when the entire Earth turned into a single eye, peering 55 million light-years in the void to see a shadow 3 times the size of our solar system. Crossing the event horizon is not the first danger you would face. Long before you reach that point of no return, you would encounter a force so bizarre it has earned a name straight from a cosmic horror story, spaghettification. This is not science fiction, but the brutal reality of extreme tidal forces. Gravity weakens with distance, so the pull on your feet, closer to the black hole, would be unimaginably stronger than the pull on your head. The difference would not be a gentle tug. It would be a violent, unstoppable stretching force. You would be elongated, pulled into a long, thin strand of atoms, resembling a piece of spaghetti. Every molecule in your body would be ripped apart in a line, a process physicists call, with grim accuracy, tidal disruption. To understand the scale, consider the gentle tides on Earth. The moon's gravity pulls slightly harder on the side of our planet facing it, stretching the oceans to create high tide. This force is so subtle we never feel it. Even near a neutron star, the incredibly dense remnant of a star, the tidal forces are fierce enough to shred a planet, but they are concentrated over a larger area. At a stellar mass black hole, however, the gravity is so intense and the object so compact that the change and pull over just the height of your body is catastrophic. The gradient is lethally steep. One moment you are whole, the next you are a stream of elementary particles spiraling into the abyss. It is a reminder that the universe is not merely empty space, but a landscape sculpted by forces that operate on a scale far beyond human experience, forces that can turn reality itself into a filament of doom. This warping of space has a direct and mind-bending consequence for time itself. Einstein's theory of general relativity taught us that gravity does not just bend the path of light, it also bends the very flow of time. This phenomenon is called gravitational time dilation. The stronger the gravity, the slower time passes relative to a weaker gravitational field. Near a black hole, where gravity is at its most extreme, this effect becomes not just measurable, but profound. Picture a thought experiment. You are in a safe spacecraft, watching from a distance as a volunteer in another ship, equipped with a powerful clock that beams its ticks back to you, begins a slow, controlled descent toward the event horizon. From your perspective, something strange happens. The clock's ticks, transmitted by light, start to arrive further and further apart. The clock appears to be ticking slower and slower. As the volunteer's ship gets agonizingly close to that invisible boundary, The ticks stretch out into an infinite silence. The clock and the volunteer seem to freeze in time, hovering forever at the edge of the black hole's shadow from your point of view. This is not an illusion of light or a trick of the signal. Time itself, for the volunteer, is actually passing at a different rate than it is for you. For them, the clock ticks normally inside their ship. They would experience crossing the event horizon in a finite amount of their own time, perhaps just a few moments after they pass the point of no return. But from your distant vantage point, you would never see them cross. The last image of them, redshifted into oblivion, would be eternally stuck at the threshold. This means a black hole's history, as seen from the outside universe, is painted on its event horizon, a frozen gallery of everything that ever fell in. It presents a bizarre cosmic paradox, where an event can be both finite for one observer and infinite for another, challenging our most basic intuition about cause and effect. This frozen paradox leads to an even more dizzying possibility. If you could somehow construct a ship of unimaginable strength and hover just outside the event horizon, resisting the pull, you would experience time dilation at its most extreme. From your perilous vantage point, time in the outside universe would appear to rush forward at an incredible rate. The clocks of every star, every galaxy, would spin like the hands of a frantic stopwatch. In what felt like just a few hours or days of your own experienced time, you could watch entire civilizations rise and fall on distant worlds. You would witness stars being born, burning through their fuel, and dying in spectacular supernova, all in a blur of cosmic light. In a matter of weeks, you might see our own sun swell into a red giant, engulfing the inner planets, before cooling into a white dwarf. Given enough time in your precarious position, you could theoretically witness the entire future history of the universe unfold before your eyes. You would see galaxies collide and merge, watch as the last stars flicker out, and observe the cosmos enter its dark, cold, final era, all within a single human lifetime of your own perception. This is not time travel, but a brutal manipulation of time's flow by gravity. The catch, of course, is absolute and terrifying. This is a one-way observation post. While you are watching aeons pass in moments, you are also using up the last of your own time. Any step away from the black hole is impossible, as you are fighting the most powerful gravity in existence just to stay in place. The moment your ship's engines fail, you cross the threshold and are lost. So you would be trading your own future for a front row seat to the future of everything else, a spectator to the end of time itself, forever separated from the universe you are observing. The universe is not a still life, and neither are its monsters. While we often picture black holes as static pits, the reality is far more dynamic. Most black holes are likely spinning, and some are whirling at a significant fraction of the speed of light. These are known as Kerr black holes, named after the mathematician who solved Einstein's equations for a rotating black hole. This spin does not just affect the matter falling in, it warps the very fabric of reality around it. The black hole's immense rotation drags the surrounding spacetime along with it. Like a spinning ball submerged in thick honey would twist the honey around itself. This bizarre phenomenon is called frame dragging. The effect is so powerful that it creates a region just outside the event horizon called the ergosphere, a flattened, pumpkin-shaped zone of distorted spacetime. Within the ergosphere, spacetime itself is being pulled sideways so violently that nothing, not even light, can remain stationary. It is impossible to stand still, no matter how powerful your rockets. You are forced to move in the direction of the black hole's spin, caught in a cosmic whirlpool. This has profound implications. The ergosphere is not a zone of certain death like the event horizon. Matter and energy can still escape from it, but only after being whipped around and gaining tremendous energy from the black hole's rotation. In theory, an advanced civilization could even use this effect to extract energy from a spinning black hole, a concept known as the Penrose process. It turns a black hole from a simple sinkhole of gravity into a colossal cosmic flywheel, storing unimaginable rotational energy in the twisted spacetime around it. Spinning black holes twist spacetime, but what if that is all they remember? For decades, physicists believed in a starkly simple principle called the no-hair theorem. The name is a metaphor. It suggests that a black hole, regardless of what complex object formed it or what messy assortment of matter fell into it, would quickly settle into a perfectly smooth, featureless state described by just three numbers: its mass, its electric charge, and its spin. Think of it like a cosmic blender. You could throw in a star, a planet, a library of books, or a grand piano. After the violent process of collapse and consumption, all that would remain is a black hole with a specific weight, a possible electric charge, and a specific rate of spin. Every other detail, every shred of information about what made it, would be irretrievably erased from our universe. The black hole would have no hair, no distinguishing features beyond those three bare quantities. This presented a profound problem known as the information paradox. In quantum mechanics, information is never truly destroyed. It may be scrambled beyond recognition, but in principle, it should always be possible to reconstruct the past from the present state of a system. The no-hair theorem seemed to violate this sacred quantum rule by offering a one-way street to oblivion. If true, it meant black holes were the ultimate shredders of reality, erasing the history of everything they consumed. But the universe rarely allows for such perfect simplicity. Recent theoretical work hints at a fascinating loophole. The concept is called quantum hair. The idea is that when matter falls into a black hole, it may leave incredibly subtle imprints on the gravitational field right at the event horizon. These are not classical features you could see, but quantum-level differences, like a fingerprint etched in the fabric of spacetime itself. This quantum hair would be a faint, preserved record of what fell in, a potential solution to the information paradox. It suggests the event horizon might not be a smooth, blank wall, but a complex holographic surface encoding the data of everything it has ever consumed, a frozen library written in the language of quantum gravity. The debate is far from settled, but it reveals a universe where even the most featureless monsters might secretly carry the ghosts of their past. Our own cosmic home, the Milky Way, is no exception to the rule of galactic monsters. At its very heart, 26,000 light-years from Earth in the constellation Sagittarius, lies a supermassive black hole named Sagittarius A star. For decades, its existence was a compelling theory, but the proof came from watching the frantic dance of stars around an invisible point. Astronomers spent years meticulously tracking the orbits of stars extremely close to the galactic center. What they saw was astonishing. These stars were whipping around at speeds exceeding 3 million miles per hour, tracing elliptical loops around absolutely nothing. The only explanation for such frenetic motion was the gravitational grip of an object with a mass over 4 million times that of our Sun, all crammed into a region smaller than our solar system. The math was undeniable, the conclusion inescapable. A supermassive black hole was the only possible anchor for this stellar carousel. Today, Sagittarius A star is relatively quiet, a slumbering giant. Unlike the violent quasars of distant galaxies, It is not actively feasting on vast amounts of material, and therefore does not shine with intense radiation. But do not mistake its quiet for impotence. Its gravitational influence is the silent conductor of our galaxy's grand symphony. It is the central weight that helps bind the Milky Way's spiral arms together, influencing the orbits of billions of stars, including our own Sun. Every 230 million years, our solar system completes one leisurely orbit around this distant, dark monarch. Its presence is the reason we are here at all, for it provided the gravitational seed around which our galaxy first coalesced. We live in the peaceful suburbs of a realm ruled by an invisible, sleeping titan. Yet even a quiet giant can awaken. When a supermassive black hole begins to feed, it does not do so subtly. It becomes the engine for the most persistently luminous objects in the known universe, quasars. The term itself means quasi-stellar radio source because when first discovered, they appeared as single, star-like points of light, but their radio emissions were off the charts. We now know a quasar is the blazing core of a distant galaxy, powered entirely by a voracious supermassive black hole. The process is one of terrifying beauty. Imagine a vast whirlpool of gas, dust, and even entire stars, drawn inexorably toward the event horizon. This material does not fall straight in, but forms a flattened, superheated structure called an accretion disk, spinning at nearly the speed of light. Friction and tidal forces within this disk heat the matter to millions of degrees, causing it to glow with the intensity of 1 trillion suns. This is not the black hole itself shining, of course, but the last, furious scream of light from matter just outside the point of no return. The luminosity is so staggering that a single quasar can outshine its entire host galaxy of hundreds of billions of stars. For a time, the black hole's feast becomes a cosmic lighthouse, visible across billions of light years. We see many quasars at immense distances, meaning we are seeing them as they were when the universe was young. They are beacons from the dawn of time, revealing an era when black holes grew rapidly by consuming the rich gas of early galaxies. But the spectacle does not end with the disk. Often, along the black hole's spin axis, perpendicular to the accretion disk, some of the infalling material gets channeled and blasted outward. These are relativistic jets, narrow beams of particles and radiation accelerated to nearly light speed. They can stretch for hundreds of thousands of light years, far beyond the bounds of their host galaxy, punching into intergalactic space. When one of these jets is pointed nearly at Earth, we see an even more extreme object called a blazar, a source of some of the highest energy photons and cosmic rays we detect. So from a point of absolute darkness comes a paradoxical fountain of light and energy, shaping not just its own galaxy, but the space between galaxies for millions of light years around it. But the giants we can see may be only half the story. The universe's first black holes might have been unimaginably small, born not from dying stars, but from the chaotic furnace of the Big Bang itself. These are primordial black holes, hypothetical relics from the universe's first fraction of a second. In that moment of extreme density, random fluctuations in the hot, dense soup of matter and energy could have created pockets so dense they directly collapsed. Unlike stellar black holes, these could have formed with almost any mass, from mountain size to smaller than a single atom. A primordial black hole with the mass of a large asteroid could be no wider than a single proton. This leads to a startling possibility. If vast numbers of these tiny, ancient black holes were created, they could be drifting unseen throughout the cosmos right now, even through our solar system. They would be nearly impossible to detect directly, as their microscopic event horizons would swallow very little light. This makes them a compelling, though unproven, candidate for the mysterious substance known as dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have never identified what it actually is. Could it be that a significant portion of the universe's missing mass is actually a diffuse sea of these primordial pinpricks of gravity? The idea is both elegant and unsettling. It would mean that right now, as you watch this, one of these atom-sized black holes could be passing straight through the Earth and through you without a trace. Because they are so incredibly tiny, they would zip through the vast empty spaces inside atoms, rarely interacting with anything. You would never feel it. It is a ghostly thought that the fabric of reality might be threaded with countless invisible fossils from the moment of creation, each a silent testament to the universe's violent birth. Those silent, drifting ghosts would remain forever hidden, were it not for the most violent events in the cosmos. Black holes are not always solitary hunters. They can find each other, locked in a gravitational embrace that ends in a cataclysm so powerful it does not just release light, but shakes the very structure of reality. This is the merger of binary black holes. Imagine two of these invisible titans, perhaps the remnants of massive stars that once orbited each other in life, now circling one another in a silent, accelerating dance. As they whirl, they lose energy by radiating it away in a form predicted by Einstein a century ago, gravitational waves. These are not waves of light or sound, but literal ripples in the fabric of spacetime itself. Think of the universe as a vast, still pond. The black holes are like two heavy weights spinning on its surface. Their immense motion creates ripples that propagate outward at the speed of light, stretching and compressing space itself as they pass. For billions of years, this was pure theory. Then, on September 14, 2015, humanity heard the universe for the first time. The Laser Interferometer Gravitational Wave Observatory, or LIGO, a pair of exquisitely sensitive detectors in the United States, recorded a faint chirp. It was the signal of two black holes, one about 29 times the mass of our Sun and the other 36 times, spiraling inward at nearly half the speed of light, and finally merging into a single, more massive black hole. In that final fraction of a second, an amount of energy equivalent to 3 times the mass of our Sun was converted directly into gravitational waves, a burst of power that briefly outshone every star in the observable universe combined. That chirp was the sound of space-time ringing like a bell. It confirmed a new sense for astronomy, allowing us to hear the collisions of objects that emit no light at all, opening a window into the dark universe. That gravitational wave chirp was a new kind of cosmic whisper, but it was not the only way we have heard a black hole. In a more haunting and direct way, we have listened to one sing. In 2022, NASA released an audio clip that swiftly captivated the internet, described as the sound of the black hole at the center of the Perseus galaxy cluster. The reality is both more scientific and more profound. For decades, astronomers knew that the supermassive black hole in Perseus was sending out immense pressure waves through the hot gas that fills the cluster. These are actual ripples in the gaseous medium, similar to sound waves here on Earth, but they occur on a scale so vast, and at a pitch so low they are completely inaudible to human ears. The note they correspond to is about 57 octaves below middle C. To put that in perspective, a piano has only 7.5 octaves. This note had been rumbling through space for hundreds of millions of years, a cosmic bass note too deep for any instrument to play. NASA's scientists performed a process called sonification. They took the astronomical data from the Chandra X-ray Observatory, which maps those pressure ripples, and scaled the frequencies upward by a staggering factor of 288 quadrillion. They raised the pitch into the range of human hearing. What emerged was not a melody, but a deep, resonant, and undeniably eerie hum. It is the sound of data-given voice, a translation of a physical phenomenon we could never otherwise perceive. That haunting drone is the black hole's impact on its environment made audible, a reminder that the universe operates in frequencies far beyond our natural senses, and that with ingenuity, we can listen to the music of the spheres, even when the conductor is a monster of pure gravity. That haunting sound is a testament to a black hole's power, but even these cosmic giants are not eternal. Stephen Hawking proposed a revolutionary idea that turned our understanding on its head. Black holes, he theorized, can actually evaporate. This process, known as Hawking radiation, emerges from the bizarre marriage of quantum mechanics and gravity right at the event horizon. In the quantum vacuum, space is not truly empty. It is a seething foam where pairs of particles and their antimatter counterparts, like an electron and a positron, constantly wink in and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other and paying the energy back. Normally, this happens everywhere with no net effect, but at the very edge of a black hole's event horizon, a strange theft can occur. One of these virtual particles can fall across the threshold, while its partner escapes into space. The escaped particle becomes real, stealing a tiny amount of energy from the black hole's gravitational field to do so. To balance the cosmic books, the black hole itself loses a correspondingly tiny amount of mass. From the outside, it appears the black hole is radiating, slowly leaking energy particle by particle. For a stellar mass black hole, this process is so unimaginably slow it is almost meaningless. The temperature of the radiation is inversely related to the black hole's mass, meaning larger black holes are actually colder. A black hole with the mass of our Sun would have a temperature barely above absolute zero, and it would take about 10 to the power of 67 years, a number with 67 zeros, to evaporate. That is timescales so vast they dwarf the current age of the universe by many orders of magnitude. For now, black holes are growing far faster from accretion than they are shrinking from this faint quantum whisper. But for the very smallest theoretical black holes, the story is different. A primordial black hole with the mass of a small mountain would be hot, radiating intensely and evaporating in a final, explosive flash of gamma rays. Hawking radiation suggests that even the darkest prisons in the universe have a tiny, quantum-sized leak, a promise that given enough time, even the mightiest monsters will one day fade away. Hawking radiation paints a picture of a slow, quiet death, but its final act is anything but gentle. As a black hole loses mass through this quantum leak, a strange reversal occurs. Remember, the temperature of the radiation is tied to the black hole's size. The smaller it gets, the hotter it becomes. So as it evaporates, it does not fade away calmly. It begins to evaporate faster and faster, growing hotter in a runaway feedback loop. In its final moments, a stellar mass black hole is irrelevant, as its lifetime is longer than the current age of the universe. But for a hypothetical small black hole, perhaps a primordial one with the mass of a mountain, the end would be a spectacular flash. Imagine that last fraction of a second. The black hole, now microscopic, would have a temperature soaring into the billions of degrees. The faint quantum whisper of Hawking radiation would become a shriek. It would transform into a torrent of every known kind of particle and radiation. from gamma rays to electrons, all blasting outward in a final, defiant burst. The energy released in that instant would be staggering, equivalent to the detonation of millions of 1 megaton nuclear bombs. It would be a tiny, ultra-powerful explosion, a white-hot flash of creation emerging from the heart of destruction. We have never observed such an event, and it is possible primordial black holes of this size do not even exist, but the theory suggests a profound cosmic irony. The ultimate symbol of gravity's absolute dominance would meet its end not with a collapse, but with an eruption, a conversion of its last remnants into a firework of fundamental particles, returning its borrowed mass energy back to the universe in one brilliant terminal pulse. Even that final explosive flash would be an indirect signal, a last message from an object we could never truly look upon. The most fundamental truth about a black hole is also the most frustrating for astronomers. You cannot see one directly, ever. By their very definition, they emit no light of their own. No photons, no radio waves, no X-rays can climb out of that gravitational prison to reach our telescopes. So how do we study something that is, by nature, invisible? We become cosmic detectives, observing the crimes of gravity. We look for the evidence they leave behind in their neighborhood. The first and most classic method is to watch the motion of objects nearby. Just as you might infer the presence and size of a hidden magnet by watching how iron filings dance around it, we watch stars. The frantic, high-speed orbits of stars at the galactic-center, whipping around an empty point, were the definitive proof of Sagittarius a star. Their paths, traced over years, paint an invisible mass in the negative space of their motion. Another telltale sign is the scream of doomed matter. When gas from a companion star or a nebula spirals into a black hole's accretion disk, it is heated to millions of degrees. At such temperatures, it glows not in visible light, but in high-energy X-rays. Satellites like Chandra scan the heavens for these brilliant, pinpoint X-ray sources, which often betray a black hole's location as it actively feeds. Then there is gravitational lensing, one of Einstein's most elegant predictions. A black hole's immense gravity warps the space around it, acting like a cosmic magnifying glass. If a black hole passes directly between us and a distant star, it can bend and focus the star's light, causing a temporary brightening and distortion. We see the shadow of the black hole's gravity on the starlight. And now, of course, we have the Event Horizon Telescope's image. But even that iconic orange ring is not a direct photograph of the black hole. It is a picture of the absence of light, the dark shadow cast against the brilliant backdrop of its superheated accretion disk. It is the silhouette of the event horizon, a shadow puppet on the wall of the universe. Every single piece of evidence we have is circumstantial, a footprint in the sand. We are forever studying the ghost by the shape of the door it slams shut. This footprint in the sand, this shadow on the wall, can sometimes become a cosmic magnifying glass. A black hole's gravity is so intense it does not just trap light. It bends the very path that light travels through space. This phenomenon is called gravitational lensing, and it is one of the most direct proofs of Einstein's vision of curved spacetime. Think of it this way. Place a heavy, clear marble on a printed page. The words beneath the marble will appear distorted and magnified, stretched around its curved surface. A black hole does the same thing to the fabric of the universe, but on a titanic scale. When a black hole sits directly between us and a distant star or galaxy, its gravity warps the space around it. The light from that background object, traveling toward us in a straight line, finds its path curved as it passes through this warped region. From our perspective, the light appears to be coming from a different direction. The result is not a single, clear image. Often, we see multiple images of the same distant object, arranged in a ring or arc around the black hole's location. In a perfect alignment, where the black hole, the background star, and our telescope are in a straight line, the warping creates a complete circle of light called an Einstein ring. It is a halo of distorted reality, a perfect geometric signature of immense mass bending the paths of photons. This lensing effect is not just a cosmic curiosity, it is a powerful tool. It acts as a natural telescope, provided by the universe itself. The bending and focusing of light can magnify distant objects that would otherwise be far too faint to see. Astronomers have used this technique to observe some of the earliest galaxies, their light amplified by the gravitational field of an entire cluster of galaxies, often anchored by a supermassive black hole in the foreground. But the lensing reveals something even more mysterious. The amount of bending we observe often requires more mass than we can account for from the visible stars and gas. This invisible mass, which reveals itself only through its gravity, is the signature of dark matter. By mapping how black holes and galaxy clusters distort the light from background galaxies, we are essentially mapping the distribution of this unseen material. We are using light, bent by gravity's hand, to draw a picture of the universe's greatest hidden component. So a black hole becomes more than a monster, it becomes a probe, a lens through which we see the invisible architecture of the cosmos. This cosmic lens reveals a universe of structure, but at its heart lies a contradiction so deep, it threatens to unravel our understanding of physics itself. The information paradox is not a minor puzzle, it is a fundamental crisis. It begins with two pillars of modern science that work perfectly in their own domains, but create a logical nightmare when they meet at the edge of a black hole. On one side, we have quantum mechanics, the rules governing the very small. A core principle of quantum theory is that information is never truly destroyed. It can be scrambled, hidden, or transformed, but in principle, if you knew the exact quantum state of every particle in the universe right now, you could theoretically rewind the tape. You could reconstruct everything that ever happened. Information, in this sense, is the ultimate historical record, and quantum mechanics insists it must be preserved. On the other side stands general relativity, Einstein's theory of gravity. It describes black holes with elegant simplicity, culminating in the no-hair theorem. As we discussed, this theorem says a black hole is defined only by its mass, spin, and charge. Throw a library, a spaceship, or a star into it, and all the unique details of those objects, the information that made them what they were, is utterly erased from our universe. The black hole does not care. It smooths everything out into a featureless pit. So here is the paradox. Quantum mechanics says information must be saved. General relativity, through the black hole, says information is permanently deleted. Both theories cannot be correct. This is not a small mathematical disagreement. It is a direct clash at the frontier of reality, suggesting our foundational laws of physics are incomplete. For decades, physicists have wrestled with potential solutions, each more bizarre than the last. One leading idea comes from the holographic principle. It proposes that all the information about what fell into the black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a hologram on a flat surface. The three-dimensional interior is a projection from that data. Another, more violent proposal is the firewall hypothesis. It suggests that instead of a smooth, empty space at the event horizon, there exists a literal wall of blazing high-energy particles. Anything crossing would be incinerated before it could pass the point of no return. This firewall would preserve information by preventing anything from actually entering the black hole in the first place. But it violates Einstein's principle that someone falling in should feel nothing special as they cross. The paradox forces us to ask, is our concept of spacetime itself an illusion that breaks down under such extreme conditions? The answer, when it comes, will not just tell us about black holes, it will rewrite our understanding of reality itself. If information cannot be destroyed, perhaps it must go somewhere. The equations of general relativity are mathematically symmetrical, and this symmetry opens a door to a truly bizarre counterpart, the white hole. While a black hole is a one-way street into oblivion, a white hole would be its exact theoretical opposite, a region of spacetime from which matter and energy can only erupt outward. Nothing, not even light, could ever cross its boundary inward. It would be a cosmic fountain of pure creation, a source that cannot be fed. The idea emerges naturally from the same math that predicts black holes. If you take Einstein's field equations and run them backward in time, a black hole's event horizon, a point of no entry, becomes a white hole's horizon, a point of no exit. It is an elegant piece of theoretical physics, but whether such an object could exist in our universe is a profound mystery. One speculative possibility is that a white hole could be the other end of an Einstein-Rosen bridge, more commonly known as a wormhole. In this model, the black hole's singularity might connect to a white hole's singularity in another part of the universe, or even in another time, creating a tunnel through spacetime. Matter falls into the black hole here and is spewed out of the white hole there. Another, even more radical idea suggests the Big Bang itself could be viewed as a primordial white hole event, a single point of spacetime erupting into the entire cosmos. Yet for all their theoretical intrigue, white holes face a monumental problem: thermodynamics. Our universe overwhelmingly favors an increase in disorder or entropy. A white hole, which would seem to concentrate energy and order, appears to violate this fundamental arrow of time. No compelling evidence for a white hole has ever been observed, and most physicists consider them unlikely to exist in our classical universe. They remain a fascinating ghost in the machine of general relativity, a reminder that the math of reality sometimes paints pictures of worlds that may be possible only on paper, or that require a complete rewriting of physics to become real. That theoretical white hole could be the exit of a cosmic shortcut, a wormhole. This staple of science fiction has a real, if fragile, foundation in Einstein's equations. Formally called an Einstein-Rosen bridge, it is a theoretical tunnel through the fabric of spacetime itself. The concept suggests that the intense curvature created by a black hole's singularity might not be a dead end, but could instead connect to another point in the universe, or even to another time, via a narrow throat. In the simplest model, you would have a black hole at one end, a white hole at the other, and a tunnel or bridge between them. This would not be a journey through normal space, but a puncture through the underlying geometry of reality, offering a shortcut across unimaginable distances. The mathematics allows for it, painting a picture of a universe stitched together with hidden threads. But the leap from a mathematical possibility to a physical reality is vast, and the obstacles are monumental. First, any such wormhole predicted by classical general relativity would be catastrophically unstable. The moment even a single photon tried to pass through, the tunnel would snap shut like a rubber band, crushing anything inside. To be traversable, the wormhole would need to be propped open, held against the crushing force of its own gravity. This is where physics ventures into the speculative. The hypothetical material needed is called exotic matter. This is not just rare or unknown matter, but something with a truly bizarre property, negative energy density. In simple terms, normal matter creates positive gravity, attracting things. Exotic matter would create negative gravity or repulsion. A lining of this substance inside the wormhole's throat could, in theory, keep it open long enough for something to pass through. The problem is, we have no evidence such exotic matter exists or could be manufactured in the quantities required. Furthermore, even if you could stabilize it, navigating a wormhole would be fraught with peril. The radiation and tidal forces within would likely be lethal, and there is no guarantee the other end would be somewhere hospitable, or even someone hospitable. For now, wormholes remain a beautiful ghost in the equations, a tantalizing reminder that the universe's rulebook might permit shortcuts we are utterly unequipped to take. The terrifying image of a black hole as an unstoppable cosmic vacuum cleaner is one of the most persistent fears. It is a vision of an all-consuming force that sweeps across galaxies, swallowing everything in its path. But this fear, while understandable, is based on a fundamental misunderstanding of gravity. A black hole is not a magical entity with a special, hungry kind of pull. Its gravity obeys the same universal rules as the gravity of a star or a planet. The only difference is its concentration. Imagine our Sun. Its gravity holds our planet in a stable orbit from 93 million miles away. Now, imagine we could magically compress the entire Sun down into a black hole with the exact same mass. What would happen to Earth? The answer is remarkably nothing. Our orbit would not change. The gravitational pull we feel from that solar mass black hole, from our same 93 million mile distance, would be precisely identical to the pull we feel from the Sun today. We would continue to circle that point of absolute darkness on the same yearly schedule, plunged into permanent night but otherwise stable. The overwhelming, inescapable force of a black hole's gravity only becomes dominant when you venture extremely close to its event horizon. It is a short-range weapon of immense power. From a distance, it is just another mass in the cosmos. You could, in theory, orbit a black hole just as you orbit a star, provided you maintained a safe and respectful distance. The danger is not in its long-range appetite, but in straying too close to its point of infinite density. So the universe is not filled with invisible roaming predators that suck in everything around them. They are anchors, not vacuum cleaners, and their terrifying power has very strict borders. Yet this safe distance is a boundary that some stars cross in a perilous, beautiful partnership. Across our galaxy, binary systems exist where a massive star and a black hole are locked in a gravitational waltz. A cosmic dance where one partner is an invisible predator. The most famous of these is Cygnus X1, the first object ever widely accepted as a black hole. In this system, a brilliant blue supergiant star, many times more massive than our Sun, orbits an unseen companion every 5.6 days. That companion, inferred from the star's motion, has a mass over 20 times that of our Sun, yet emits no light. It can only be a black hole. Their dance is intimate and destructive. The black hole's immense gravity pulls stellar wind and gas from the surface of its massive partner. This stolen material does not fall straight in, but spirals into an accretion disk around the black hole, heating to millions of degrees and glowing fiercely in X-rays. From our vantage point, Cygnus X1 appears as a brilliant, flickering beacon in the X-ray sky, the scream of the star's stolen atmosphere. These black hole binaries are not just cosmic curiosities, they are essential laboratories. By studying the orbit of the visible star, we can weigh the black hole with precision. By analyzing the flicker and spectrum of the X-rays, we can probe the physics of the accretion disk, matter moving at relativistic speeds just outside the event horizon. They allow us to test Einstein's predictions in extreme environments, watching how gravity behaves when a star is literally being consumed by its dark partner. This dance is always one-sided, a slow cosmic feast. Over millions of years, the black hole will siphon away more and more of the star's mass, potentially leaving behind a stripped core or consuming it entirely. For now, they whirl through space together, a luminous star and an invisible pit, painting a vivid portrait of gravity's dual nature, both a binding force and an instrument of annihilation. That intimate dance of binary systems takes place on a scale we can almost comprehend. But the universe also forges monsters that defy all sense of scale. At the very edge of our observable cosmos lies an object of such staggering proportions it redefines the word giant. Ton 618 is not just a supermassive black hole. It is a hyperluminous quasar, and at its heart lies a gravitational singularity estimated to weigh 66 billion times the mass of our Sun. To grasp that number, try to picture our entire solar system. Now, imagine the event horizon of this black hole, the point of no return for light. That boundary would not just swallow the Sun and the planets. It would extend outward over a distance of more than 1,300 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. This means Ton 618's event horizon would stretch far beyond the orbit of Pluto, engulfing the entire Kuiper belt and much of the scattered disk, a sphere of darkness larger than most solar systems we know. The accretion disk feeding this behemoth shines with the luminosity of 140 trillion suns, making it one of the brightest single objects in the known universe. But its immense size presents a profound cosmic puzzle. We see Ton 618 as it was over 10 billion years ago, when the universe was only about 1/4 of its current age. This forces a daunting question upon us. How did a structure this colossal, requiring the consumption of unimaginable amounts of matter, assemble itself so quickly after the Big Bang? The standard models of black hole growth, through steady accretion and mergers, struggle to explain how such a titan could have formed in what was, cosmically speaking, the blink of an eye. It suggests either that the early universe provided a feast of density we have yet to fully understand, or that the seeds for these monsters were planted by something even more exotic, like the direct collapse of enormous gas clouds into black holes without ever becoming stars first. Contemplating Ton 618 is to stare into a paradox of time and gravity, a relic from the dawn of creation that already wielded the power to dictate the fate of an entire galactic region. The sheer scale of a titan like Ton 618 forces a question about its purpose. Is such a monster merely a passive sinkhole at a galaxy's heart, or does it actively shape its entire cosmic home? The answer is rewriting our understanding of galactic ecology. Supermassive black holes are not just residents of galaxies, they are regulators, wielding a surprising power over the birth of stars across billions of light years. This process is known as feedback, a cosmic balancing act between creation and suppression. When a supermassive black hole feeds vigorously, becoming an active quasar, it does more than just shine. The tremendous energy released from its accretion disk and the relativistic jets shooting from its poles flood the surrounding galaxy with radiation and heat. This energy pours into the vast reservoirs of cold molecular gas, the raw material for new stars. Imagine a nursery filled with sleeping infants, where a sudden, blaring alarm clock prevents any of them from settling into a deep sleep. The black hole's outburst heats the gas, preventing it from cooling down, collapsing under its own gravity, and condensing into new stellar nurseries. In essence, the central monster can put the brakes on the very process that built its host galaxy. This quenching effect is thought to be the primary reason why massive elliptical galaxies, often found at the hearts of dense galaxy clusters, are red and dead, filled with old red stars and devoid of the blue light of new star formation. Their black holes, through immense outbursts in the distant past, have effectively sterilized their environments, shutting down the galactic factory. This creates a fascinating feedback loop. A galaxy provides gas to feed the black hole. The black hole's furious activity then heats the remaining gas and may even blow it entirely out of the galaxy, starving both future star formation and its own future meals. It is a self-regulating cycle, a gravitational thermostat that prevents galaxies from growing too large too fast. The most violent events in the universe, therefore, are not just spectacles of destruction, but essential mechanisms for cosmic order, ensuring a diversity of galactic lives and deaths across the eons. That galactic thermostat operates over eons, but from a certain vantage point, you could witness its entire effect in an instant. Flip the perspective from our earlier discussion of time dilation. We were safe observers watching a clock slow down near the event horizon. But what would you see if you were the one brave or doomed enough to cross that boundary? If we could magically ignore the lethal effects of spaghettification, the journey inward would present a visual spectacle of staggering, paradoxical beauty. For you, the traveler, time in your own frame of reference would feel perfectly normal. Your watch would tick at its usual pace. Your heart would beat its regular rhythm. But as you fell, you would naturally look back over your shoulder, back toward the universe you were leaving behind. The light from that outside cosmos, racing to catch up to you as you plunged into ever stronger gravity, would undergo an extreme transformation. Normally, light climbing out of a gravity well gets stretched, redshifted to longer, redder wavelengths, but light falling into a gravity well gets compressed. As you accelerate inward, you would be rushing headlong toward that incoming starlight. The result is a dramatic blue shift. The entire visible universe behind you would not redden and fade, but would instead shift up the spectrum, becoming a brilliant, blinding blue. The photons would be packed with increasing energy, but the distortion goes far beyond color. The intense gravity would also act as a lens, focusing more and more light from the entire external cosmos into your field of view. The sky would not darken, it would brighten into an unbearable, focused glare. And within that glare, time would appear to speed up. You would see the clocks of the universe tick faster and faster. The orbital dances of planets would become a blur. Stars would streak across the compressed sky, living out their full life cycles in moments. Given enough depth to your fall, you could witness galaxies evolving, merging, and fading away in a spectacular, accelerated film. In your final moments before crossing the event horizon, the entire future history of the cosmos might flood into your vision in a single, overwhelming flash of blue-white light. It would be the ultimate cosmic movie, played at 1,000,000,000,000 times normal speed. A gift of perception granted only at the price of your own destruction. You would see eternity in an instant, a private screening of the universe's destiny just for you, in the last seconds of your existence. That final, private vision of eternity relies on a critical cosmic veil, the event horizon. But what if that veil could be torn away? At the very core of every black hole lies the singularity, a point of infinite density where the known laws of physics cease to function. Space and time, as we understand them, simply break down. In our standard model, this monstrous flaw in reality is always hidden, forever shrouded behind the event horizon's protective curtain. This is known as the cosmic censorship hypothesis, a rule that the universe politely conceals its own infinities from view. However, some solutions to Einstein's equations suggest a terrifying possibility, a naked singularity. This would be a gravitational singularity completely exposed to the rest of the universe, with no event horizon to hide it. Think of it as a raw wound in the fabric of spacetime, a point where gravity becomes infinite, visible for all to see. The implications are not just strange, they are catastrophic for physics as we know it. With a naked singularity, the predictable cause and effect universe we rely on would vanish. The equations of general relativity, which normally give us clear predictions about how matter and energy behave, would simply spit out nonsense, infinite and undefined results. You could not predict what would happen to an object approaching such an exposed point. Would it be destroyed? Would it emerge somewhere else? The laws of physics would offer no answer, because at that point, there are no laws. One theoretical way to create such an abomination is through extreme rotation. If a black hole spins fast enough, the mathematics suggests its event horizon could shrink to a point and vanish, leaving the singularity naked. While most physicists believe some unknown quantum gravity effect would prevent this from ever happening in reality, the mere possibility forces us to confront the limits of our knowledge. A naked singularity would be a window into a realm without rules, a place where anything becomes possible, and that is perhaps the most unsettling prospect of all. This exposed wound in reality, a naked singularity, is the ultimate warning sign. It tells us our current map of physics is incomplete, missing a crucial piece that can describe the universe at its most extreme. That missing piece is the holy grail of modern physics, a theory of quantum gravity. And black holes are not just a problem for such a theory, they are the perfect and perhaps only laboratory where we can test our ideas. This is because a black hole is the unique crossroads where the two great pillars of 20th century science collide head-on. On one side stands general relativity, Einstein's magnificent description of gravity as the curvature of spacetime. It works flawlessly on the grand scale of planets, stars, and galaxies. On the other side is quantum mechanics, the wildly successful rules governing the behavior of atoms and subatomic particles. Both theories are spectacularly accurate in their own domains, but they are written in completely different mathematical languages and based on fundamentally different principles. They cannot both be correct at the same place at the same time. That place is the singularity at the heart of a black hole and at the quantum foam edge of its event horizon. Here, an object of immense mass is crushed into a volume smaller than an atom, forcing the rules of the very large and the very small to meet. The resulting paradoxes, like Hawking radiation and the information paradox, are not mere puzzles. They are screaming clues from nature, pointing directly to what a complete theory must look like. Hawking's discovery that black holes can radiate and evaporate was the first concrete hint that quantum effects must play a role in gravity. The information paradox is the glaring contradiction that any successful theory must resolve. To understand the fabric of reality itself, we must listen to what these dark monsters are trying to tell us. By probing their shadows, their evaporation, and the fate of information, we are not just studying black holes. We are using them as cosmic microscopes, magnifying the hidden seams between spacetime and the quantum world, searching for the single set of rules that governs everything from the birth of the universe to the spin of an electron. The singularity's infinite density is a glaring sign that our physics is broken, a mathematical warning that something must replace it. To heal this flaw, we must step beyond Einstein and into the realm of quantum gravity, where the most promising candidate, string theory, offers a radical alternative called the fuzzball. Forget a point of infinite density. In this view, a black hole is not a vacuum with a central singularity at all. Instead, the entire region inside the event horizon is filled with a gigantic, tangled ball of the universe's most fundamental ingredients, vibrating strings. These are not strings like you find on a guitar, but unimaginably tiny loops of pure energy, theorized to be the building blocks of all particles. In a fuzzball, these strings do not collapse to a point. They become a frenzied quantum knot, expanding to fill the entire volume where we thought there was nothing. The event horizon becomes not a sharp boundary, but a fuzzy, transitional surface where this tangled ball of strings ends. This idea elegantly solves several problems at once. First, it banishes the nonsensical singularity. There is no point of infinite density, just a very dense but finite ball of quantum stuff. Second, and more profoundly, it could resolve the information paradox. Every unique configuration of the tangled strings inside the fuzzball corresponds to a unique history of what fell in. The information is not lost. It is preserved in the complex quantum state of the fuzzball itself. The black hole's interior becomes a library, not a shredder. While we cannot peer inside to read it, the information is theoretically still there, saving quantum mechanics from its crisis. Another speculative idea comes from loop quantum gravity, a different approach to unifying the cosmos. Here, the proposal is the Planck star. Imagine the collapsing core of a dying star. In classical physics, nothing stops the crush, but loop quantum gravity suggests that at the tiniest possible scale, the fabric of spacetime is granular, made of discrete loops. When matter is compressed to this scale, a new repulsive force emerges from the quantum structure of space itself, like a cosmic spring. The collapse would not end in a singularity, but would rebound. The dying star would shrink to an incredibly dense ball, perhaps the size of an atom, but containing the mass of several suns, and then bounce back outward. From the outside, we would still see an event horizon and a black hole, but inside, the story is completely different. There is no point of no return, just an incredibly dense, bouncing core. This bounce would be so slow, due to extreme time dilation, that it could take billions of years from our perspective. In a sense, a black hole could be a star in suspended animation, waiting to explode back out into the universe. These are not proven theories, but they are vital thought experiments. They show us that the terrifying infinite pit might be an illusion, a placeholder for a physics we are only beginning to glimpse. That glimpse of a fuzzball or a bouncing star remains pure theory, but we are on the verge of seeing a black hole's reality in motion. The Event Horizon Telescope's first image was a historic snapshot, a single frame in the life of a cosmic monster. The next step is to turn that snapshot into a movie. This is not science fiction, but an active, monumental effort in observational astronomy. The goal is to record a video of a black hole's shadow, capturing how its turbulent accretion disk and the silhouette of its event horizon change over hours, days, and months. Think of it like trying to film a whirlpool from the edge of a distant shore. You would not just see a static circle of water, but the churning motion, the way the currents shift and spiral. For a black hole, that motion is matter orbiting at nearly the speed of light, heated to billions of degrees. Capturing this requires more than just patience. It requires transforming our entire planet into a more sensitive eye. The original image of Messier 87's black hole used data from just 8 telescopes over a few nights in 2017. To make a movie, scientists need more telescopes in the global array to collect data faster, creating multiple frames. They also need to observe for longer periods, tracking the black hole across multiple years. The technical challenges are staggering, involving synchronizing observatories across continents, processing oceans of data, and developing new algorithms to stitch together a coherent moving picture from sparse measurements. But the scientific payoff would be revolutionary. A movie would show us the dynamic behavior of spacetime itself. We could watch blobs of superheated plasma orbit the event horizon, tracing the paths dictated by extreme gravity. We might see the shadow wobble and flicker as new material falls in, or witness the powerful magnetic fields that channel matter into relativistic jets. It would be a direct test of Einstein's predictions in a dynamic, violent environment, showing us not just that black holes exist, but how they live, breathe, and feed. We would move from studying a portrait to observing the beast in its natural habitat. These cosmic architects have left their signature across the largest canvas imaginable. The universe is not a random scattering of stars and galaxies, but a vast, intricate tapestry known as the cosmic web. Picture an enormous spiderweb with dense clusters of galaxies at the intersections, connected by long filaments of gas and dark matter, and separated by immense, empty voids. This is the large-scale structure of our cosmos, and supermassive black holes have been instrumental in weaving it. Their role begins in the early universe, when the first giant black holes ignited as brilliant quasars. The incredible energy from these beacons and their powerful jets heated the diffuse gas that filled the spaces between galaxies, preventing it from cooling and collapsing to form new, small galaxies in the voids. This process helped define the boundaries between the dense filaments and the empty expanses, sculpting the web's very shape, but their influence did not stop there. When galaxies drift together and merge, drawn by their mutual gravity, their central black holes eventually spiral inward and collide in a cataclysmic burst of gravitational waves. These titanic mergers are the most energetic events since the Big Bang, and they can kick the newly formed, even larger black hole out of the center of the merged galaxy at incredible speeds. This recoil sends the monster plowing through its new home, stirring up gas and disrupting star formation in its wake, further altering the galaxy's evolution. Over billions of years, through countless cycles of feeding, quenching star formation, and merging, these gravitational giants have acted as regulators and sculptors. They help determine which galaxies grew massive and quiet, and which remained small and active. They influenced where stars could be born and where cosmic deserts would remain. So when you look up at the night sky, you are not just seeing points of light. You are witnessing a grand structure whose form was, in part, dictated by the silent, dark hearts at the center of it all. The black hole is not merely a resident of the universe. It is one of its master builders, a fundamental force in the story of how everything came to be arranged. From galactic architects to cosmic paradoxes, this journey has revealed black holes as far more than simple holes in space. They are the universe's ultimate laboratories, where the rules of reality are stretched to their breaking point. We have seen how they warp time into a slow-motion river, trap light in a prison of gravity, and erase information in a way that threatens the very foundations of physics. They are engines of creation, sculpting galaxies and birthing quasars that outshine entire constellations. They are silent record keepers, potentially holding the history of everything they consume in a holographic shell. And they are messengers, sending us ripples in spacetime and shadows on a cosmic backdrop, challenging us to look deeper. These 30 facts peel back the curtain on a cosmos that is stranger, more dynamic, and more interconnected than we ever dared to dream. The true wonder is not just that these monsters exist, but that by studying them, we are forced to rewrite our own understanding of existence. So tell us, which of these facts changed your perspective the most? Let us know in the comments below. If exploring the mysteries of the universe captivates you, subscribe for more journeys to the edge of understanding. And tonight, when you look up at the starry sky, remember you are gazing into a realm where darkness is not empty, but filled with the most profound questions and answers waiting to be found.